So this is the fourth and final part of the chapter 5.2, and we will talk about dynamical systems and how to use eigenvalues and eigenvectors to solve dynamical systems and make predictions. And we will start with our problem, which we saw in a couple of weeks when we tried to model of the movement of the population from city to the suburbs of some kind of region. And we know that there's a data that every year 5% of the population move from city to the suburbs, and from 3% moving from suburbs to the city. And when we work through this problem initially, we form a stochastic matrix of A, which is accounts for movement between city and the suburbs. And we are also started with what's called initial conditions, or vector x0, which has the distribution of population and at initial year, the year when we start the data collection, x0. And in the previous class, we developed a recursive formula when we calculated the year after year. But as we discussed earlier in the previous chapter, that we can use eigenvalues and eigenvectors to actually find the shortcut and calculate the distribution of the population any year without any previous calculations. But okay, let's start by finding the eigenvalues by using characteristic equation for our matrix A, which is, we take our matrix A, subtract lambda from diagonal element, and set a determinant equal 0. And because this is 2 by 2 matrix, that's pretty straightforward to calculate. You multiply elements in left diagonals and subtract product of elements on the right diagonal. And when you come back the like terms, you have a second degree polynomial, which is equal 0. So we have a quadratic equation, which we can solve using quadratic formula. And when we simplify, we find that it has two solutions, 1 and 0.92, which means that we have two eigenvalues. First one, lambda 1 is equal 1, and second, lambda 2 is equal 0.92. Let's try to find the eigenvectors which corresponds to each of the eigenvalues. We know that it can be a lot of them, so let's just start with the lambda equal 1. So our eigenvectors are just a solution of the homogeneous equation A minus lambda I. So again, we take our matrix, subtract an identity matrix, and augment it with the row of zeros. It's a homogeneous equation. Okay, so now let's try to reduce it to the echelon form, and you will find that this matrix has a free variables, and let's assume that x2 is our free variable, so we can write it down in terms of free variable x2, and we can choose any x2, any non-zero value of x2. Because I like things simple, I choose x2 is equal 1, and one of the eigenvectors, v1, I call it v1, is a correspond to x2 is equal 1, and it's 3, 5, and it's as good as any other eigenvector. Okay, so let's repeat the process for the second eigenvector equals 0, eigenvalue equals 0.92. Again, we take our matrix, subtract the lambda equals 0.92 from the every left diagonal element, augment it with a 0 row to the right, and reduce it to the echelon form. And again, we have a free variable, so again we can write it down, our eigenvector, in terms of free variable x2. And because again, just we want to have things simple, we choose value x2 is equal 1. So one of the eigenvectors is 1 minus 1. So now we have two eigenvalues two eigenvectors, and our eigenvectors are form the basis in R2. So we can take our initial vector x0 and write it down in terms of vector x v1 and v2. So basically in a basis of v1 and v2. And this basis is just a linear combination of our vectors v1 and v2. And we can just make a matrix formed by the two vectors v1 and v2 multiplied by the vectors c1 and c2, and it should be equal 0. So basically what we're trying to do here is solve this matrix equation for weights c1 and c2. And at this point of the course, you should know at least 3 different ways to solve this equation. You can use elimination, you can use the echelon form, you can use inverse matrix, you can do anything you want to solve this equation, but as final results, you should get the values of C1 and C2 is 0.125 and 0.225. Okay, so, and those weights will work for transition to any other vectors x to the basis of v1 and v2. So what if we take our vector x1 and also write it down in terms of v1 and v2? Using our recursive formula, we can write down x1 as a product of matrix A and x0. And our x0 now can be written in form in terms of the vector v1 and v2. And we can use the matrix property to distribute A matrix in both terms of this equation. And now it's worth thinking about the definition of our eigenvector. So our eigenvector times the matrix should give a eigenvalue lambda plus vector eigenvector itself. So our AV1 term over here will be exactly the same as the vector V1 times the corresponding eigenvalue lambda 1. This term AV2 over here would be exactly the same as the vector V2 times corresponding eigenvalue V2. So basically we can write it down in terms of V1 and V2 only. And we can repeat this process for the vector x2. Again, we multiply our matrix A by the vector x1, just using the definition of our dynamical systems. And again, we are replacing products of matrix by the vector by its corresponding eigenvector, eigenvalue. So, and we will get, because our first eigenvalue is equal 1, you can raise it in every power and it's remained 1, but the second terms of this equation will have a second eigenvalue 0.92 in the power 2, or it's the same power as the index of x, or our step number. We can actually kind of summarize this procedure for any number of steps. Say for the x on the step k, we can have the same, always the same term, because our eigenvalue is equal 1, C1 V1, plus our second term will be contain the product C2 V2 times the eigenvalue 0.92 in a power k. And we can actually summarize our xk. We can explicitly substitute our weights C1, C2, and our vectors V1, V2, and write down equation for our vector x for absolutely any step of k. So now, if we want to predict what's happened with the population of the city and the suburbs in 20 years from now, instead of running 20 calculations recursively, we can find the eigenvalues of our vector and conduct one single calculations to find the value of our distribution of between the city and the suburbs vector xk for any number of years coming on. Okay, that's all for this chapter, and I see you for the chapter 5.3.